Hello and welcome to another blockbuster mathematics video. In this one, we're going to start looking at Chapter 5, Section 1 in the trig book. So here's an overview of the entire chapter using fundamental trig identities, verifying trig identities, solving trig equations, sum and difference formulas, and multiple angle and product to sum formulas. So these last two sections are all about using formulas, solving equations. We've solved equations algebraically. We'll do it here with some trig functions. 5.1 and 5.2. We will have a test after 5.2, and I'll give you a warning right now. Section 5.1 might melt your brain a little bit. When we get done with 5.1, you might still be reeling and not really sure of what's going on. But when we get into 5.2, it's going to become crystal clear by the end of 5.2. I've been doing this, teaching this for over a decade. Trust me. If you're confused when we're finishing 5.1, we won't have a test after that. It will become much clearer in 5.2. Well, I like to make this analogy. Section 5.1, we are having a race, and I will not tell you what direction you're running or where the finish line is. So you're completely confused in 5.1. When we move on to 5.2, it is very, very similar material, but now it's a race where you know which way you're running and you know exactly where the finish line is. So again, bear with me. 5.1 is going to be confusing. When we get into 5.2, it's going to make much more sense. And let's dive into 5.1. The section will be cut up into 3 videos. Our bullet points here: recognize and use the fundamental identities, and use those fundamental trig identities to evaluate trig functions, simplify expressions, or rewrite trig expressions. So in the last chapter, we studied the basic definitions, the properties, the graphs, and the applications of the individual functions. In this chapter, we're going to learn how to use those fundamental identities to perform these tasks listed below: evaluate trig functions, simplify expressions, come up with additional trig identities. We don't have enough. We can always make some more. And we will solve equations that have trig functions in them. Okay. Here is a formula sheet. You have seen this before. Let's do a quick review. The top section are the reciprocals, what you flip over to get the other. So sine and cosecant are reciprocals, cos and secant are reciprocals, and as well as tan and cotan. In the middle section here, the quotient identities, just tan and cotan. This is very useful. Tan is also sine over cos. And then if we flip that over, we get cotan, cos over sine. And we know the Pythagorean identities here across the middle, the most common being sine squared plus cos squared equals 1. Down here are the cofunction identities. Remember, cofunctions of complements are equal. So if I see sine and it's cosine, sine and cos, they are going to be equal as long as I put angles in the parenthesis that are complementary. And let's do that with degrees because it's easier. If I put 10 in here, what's the complement of 10? 80. The sine of 10 and the cos of 80 are the same. I could put a 20 over here for cos. The complement of 20 is 70, so the sine of 70 and the cos of 20 are the same. So cofunctions of complements are equal. Even in odd, I like to think about, the symmetry. Well, it's just, for sine, if we have a negative angle, it's the same as the negative escaping and making the whole thing negative, but now u is positive. Cos is the opposite. The cos of a negative angle is the same as the cos of the same positive angle. It's like that negative sign got eaten up by cos. Tan is like sine. The negative can escape, migrate outside. So the tan of a negative angle is the same thing as the negative of the tan of the positive angle. Pythagorean identities, and here I'm going to abbreviate. Sine squared plus cos squared is equal to 1. Well, if I want to get sine alone and not it to be squared, I would first subtract the co-squared. So over here it would be 1 minus co-squared. And then to get rid of the squared, I would square root 1 minus co-squared. Notice the plus minus there. That depends on the choice of angle u. We would figure out what angle u quadrant lies in and figure out if sine is going to be positive or negative based on that quadrant. Okay, here we go. Example 1. One common application of these identities is to use the given info about the trig functions to evaluate other trig functions. So let's see what we got here. Use the conditions. I'm just going to copy them down here. Secant of angle u is a negative 3/2, and all they tell us other thing is the tangent is greater than 0 or tangent is positive. So the first thing I'm going to do is figure out what quadrant this angle is. So quad question mark, what quadrant is angle U in? So I'm going to set up my all students take calculus. All students take calculus. We see here that secant is negative, and if secant is negative, so is its reciprocal. So cos is less than 0. So cos is not positive. That eliminates the all quadrant and quadrant 4 where cos is positive. It says here also that tan is positive. Well, remember, tan's positive in quadrant 3, but it's not positive in quadrant 2. So we have, using those two pieces of info, figured out that we are in quadrant number 3. All right, that might come in handy later. Now it wants us to find the value of all 6 trig functions. So what I'm going to do is just make a little list over here. Sine u, cos u, tan u. So there's sine, cos, tan, and we got cotan, secant, and cosecant. And they gave us one to get us started. Secant is negative 3/2. So this is negative 3/2. We can immediately do the reciprocal cos. That'll be negative 2/3. Okay, so we're getting somewhere. They told us tan is positive, so we can put a positive in there, and that means cotan will be positive when we flip it over. And if we're in, again, we're in quadrant 3 down here, all students take, so tan is positive and it's reciprocal. That means sine is going to be negative, and I should have an equals on there. Cosecant will also be negative. So we've got 2 of the 6 done, and we've got the sines of the remaining 4. Okay, let's see what we can do here. I like to look at these first 2 as a block, sine and cos. If you have one, you can always solve for the other, because we have sine squared plus cos squared is equal to 1. Okay, and we got cos, negative 2/3. So I'm going to set a parenthesis there, and I'm going to put in that parenthesis my cos value, negative 2/3, and that is equal to 1 when we add it to sine squared. Okay, a little algebra. So sine squared of angle u plus, if we square negative 2/3, the negatives will square to a positive, and then 2/3 times 2/3 is 4/9. So that's 4/9. And then to make the work easier, I'm going to make this 1 over here into 9/9, just so we have that common denominator. Okay. Let's get the sine squared alone. This is a squared up here. So sine squared u equals, we're going to subtract the 4/9. We're going to take it over here and make it a minus 4/9. 9/9 minus 4/9 is 5/9. Okay, we're almost home on sine. If I take the square root of that, I'm going to get the sine of u equals. Now I like to root these separately because it's a fraction. The numerator is a 5, so that's just going to stay as a root of 5. But when we root the denominator, the square root of 9 is 3. So get out of there. Sine of u is root 5/3. I'm going to come up here. Root 5/3. And we've already figured out that it's negative, so we're not going to forget about that. And now, since we have sine, we can get cosecant. Let me move these out of here and erase them. Because sine, if we flip it over, becomes cosecant. So I'm going to come over here and just do a little scratch work. I'm going to have minus, and I'm going to flip that over. So now it's 3 over the root of 5. But of course, we are going to rationalize because we have good math manners. So we're going to have our negative 3 times root 5 is 3 root 5. And our denominator, root of 5 times another root of 5 is the root of 25, or just 5. Get out of there. So I don't really have room. I guess I could try to squeeze it in down here. Negative 3 root 5 over 5. And there's cosecant. The last thing is tan and cotan, and that's good to use a quotient identity on. Remember that tan is equal to sine over cos. We've got sine, we've got cos. Let's just divide them to get tan. So sine is a negative 5 over root 3. We're going to divide that by cos, negative 2 over 3. The first thing I'm going to do is do the negative divided by negative. That is going to turn to a positive. And let's bring this denominator up and flip it. So now it's 3 over 2. And on the diagonal, the 3's will cancel. So if we then multiply straight across, we're going to get a root of 5 over a 2. And that's our tan, root 5 over 2. Okay, we got tan. Let's flip it over to get cotan. So if tan is root 5 over 2, then cotan is going to be 2 over the root of 5. But once again, we've got a radical downstairs in the denominator, so we're going to multiply the numerator by that radical, and then that means our denominator is now radical free. 2 roots of 5 over 5, 2 root 5 over 5, and we already know that it is positive. So there's all 6 of the trig functions based on just knowing one of them and the sign of some other trig function, either positive or negative. Okay, up next. Ooh, or a little technology here. Ooh, or is this? This is more. We'll look at this after the next example. I'm going to move this slide. Oops. I'm going to move this slide after the next one. So here, this is what that graphing slide is going to tie into. Now here's what I mean when you're running a race and you don't know where the finish line is. Directions. Simplify the expression. Here's an expression. We could start simplifying it, but how do you know when you're done? You don't know where the finish line is. It's nice if you can get it down to a single term. Like here we've got this times this minus another term. If we can somehow get it down to one term, our job is probably done. Now, if I had shown you something like this, xy squared minus x, and I said, can you factor that? You know, you'd say, okay, there's an x in both of those terms. We can factor that out. And that's what we're looking at here. We've got a sine x minus another sine x here. So if I sort of put a set of brackets or parentheses around that, we can factor out a sine of x. So we pull a sine of x out. What's left of this first term? Well, the sine was pulled out, so we do have a cos squared. And then minus, since this sine was factored out in its entirety, we do need a placeholder 1. Okay. So we did a step, we factored something out. The directions are simplify the expression. Are we done? Again, you don't know where the finish line is. So whenever, we're going to try to train your brain to think, when you see a trig function squared and when there's a 1 floating around, either plus or minus, it might be time to use a Pythagorean identity. So I'm going to come over here and do a little abbreviated scratch work. Again, sine squared plus cos squared is equal to 1. I want to manipulate this and try to get a cos squared minus 1. Well, let's see. Over here, my cos squared is positive, so I don't want to move that to the other side. I'm going to leave this cos squared here. And if I bring this one over by subtracting it, this side is going to be cos squared minus 1. So what's going to be on the other side of equals? Well, we have to get this sine squared out of here. We're going to subtract it from both sides. So now on the other side, it's going to be a minus sine squared. So look what I underlined here in black, the cos squared minus 1. Here is cos squared minus 1. We are going to replace cos squared minus 1 with a negative sine squared x. And we have out here this sine x. Now that's not sine x minus sine squared. We are multiplying. So let's do negative times positive is negative. Sine x times sine squared is sine cubed. Sine cubed x. Now it's fully simplified. But again, you would not know exactly where the finish line is. So here again is where we started. It's pretty messy. When we're done, we're at negative sine cubed of x. Much more concise than that original expression. Now it says here we could check this by using a graphing utility. We could go into the y-editor and type in negative sine cubed of x, and it would graph out a function. And then we could also put in the y2 in the same y-editor, the original expression, sine squared cos squared minus sine x, and you would see the same graph traced over. If they have the exact same graph, they are equivalent expressions. If I plug an x value in here, I'm going to get some output. If I plug that same x value in all of these and evaluate it, I will get the exact same answer. They are equivalent expressions. Okay, a little practice for you. Very, very similar to examples 1 and 2. Okay, so pause the video at this point, try these out, and then fire it back up and see if you got the answers correct. All right, so this is just like example 1. We want all 6 trig expressions. Let me hide this more in the corner. So when we're all done, well, I'll put the x's in there. Sine x, that's supposed to be an s, sine, cos, tan, cotan, secant, cosecant. Okay, they did give us one of them. Tan is a third. So tan is 1/3. Immediately we can flip it over and get cotan, 3. And because they told us this is positive, we know for sure these are positive. So if we're going to start figuring out what quadrant we're in, all students take ceramics. We know that tan is positive, so we know that we could be in quadrants 1 or 4. So we can probably eliminate, or 2 or 1 and 3, excuse me. We can eliminate 2 and 4 because it also says here our second clue, cos is negative. So I can go over here now. I know cos is negative. That means its reciprocal secant will also be negative. And if tan is positive, that means we are not in quadrant 2. So we can also say, well, sine has to be negative. Cosecant must also be negative. Okay, so we've got these 2 in the middle. We want to expand that to all other 3. So where do we go from here? In the example, we had sine or cos, and we could use the Pythagorean for the other. So let's check our Pythagoreans. Here's our formula sheet. And remember, we have tan and cotan. So here is 1 plus tan squared. We have tan. We could use that to get secant squared. We could also use 1 plus cotan squared because we figured out cotan squared. And that could take us to cosecant. There's many ways we could go about this. So let's start with that 1 plus tan squared equals secant squared. 1 plus tan squared equals secant squared. I'm going to get a little lazy and not put my x's on there. Tan squared x, secant squared x. So let's see here. We've got 1 plus. Tan is 1/3, and we're going to square it. And that's equal to secant squared. So we have, let me do this. The 1/3, when we square it, 1/3 times 1/3 is 1/9. And we're going to add to that this one. I'm going to make that 9/9, 9/9, get that common denominator. That's equal to secant squared. And if we add our fractions, we get 10/9 is equal to secant squared. And then, of course, to get the secant down to just first power, we are going to root both sides. We'll root here, so that is secant of x. And I will do my numerator separately, root of 10. And then my denominator, root of 9, well, that's just a 3. So secant is root of 10 over 3. And we down here, we know it's negative. We already put the negative sign there. Root of 10 over 3. Okay, we've got secant. We can then do a reciprocal. If we flip over secant, that will give us cos. So if we flip that over, I'll come over here, do a little scratch work. Negative 3 over root 10. Because we have a denominator with a radical, we're going to rationalize. Multiply the numerator by a root of 10. Do the same in the denominator, and the radical disappears. So there's our cos. Negative 3, 3 root 10 over 10. Okay, let's see, what should we do next? I guess, let me see here. If we go back to that, I've done this different ways in previous years. We could do 1 plus cotan squared equals cosecant squared, because we haven't found cosecant yet. So whoa, wrong way. 1 plus cotan squared equals cosecant squared. 1 plus cotan squared equals cosecant squared. So that'll find us this, and we could flip it over to get sine. Or, since we found cos, we could do a Pythagorean sine squared plus cos squared equals 1 to get this sine squared up here. And let's stick with this one, because I like cotan is just a 3. So that'll make our computations a little easier. 1 plus cotan squared is going to be 3 squared. That's equal to cosecant squared. And if we add that up, 3 squared is a 9, plus 1 is 10. 10 is equal to cosecant squared. And when we take the root of that, we'll get root 10 is equal to cosecant of x. So down here, cosecant, we're going to put a root of 10. And remember, we already figured out it is a negative value. So that's a negative root 10. And now we can just do one final reciprocal to find that last missing piece sine. So down here, cosecant x is a negative root 10. Let's flip it over. So negative root 10, we could put a 1 under it. When we flip it, it's going to be a 1 over root 10, which is negative. And we're going to rationalize. Multiply that numerator by a root of 10. Denominator the same, and the radical disappears. So our sine value, negative, and we already knew it was negative, root of 10 over 10. And there's all 6 trig functions. Good times. Simplify. Now again, this is strikingly similar to the example we did. If I put some parenthesis around there, notice we have a cosecant and a cosecant separated by a minus in this case, so we can factor cosecant of x out. And that's going to leave a cos squared here minus, remember when we factor something out entirely, we need a placeholder 1 there to take that. Okay, so now we've got cosecant times this. Again, a little scratch work. I'm going to abbreviate. Sine squared plus cos squared is equal to 1. We again want cos squared minus 1. So here's my cos squared. It's positive. I'm going to bring over the 1 by minusing it, so that looks nice. Cos squared minus 1. What's on the other side of equals? Well, we got to move that sine squared over there where it becomes negative sine squared. So now we've got cosecant x times negative sine squared x. Okay, and again, it's hard to know when you're done simplifying because, we're running a race and we don't know where the finish line is. If you stopped there, I would not hold it against you. But there is something else we can do, because this cosecant is the reciprocal of sine. So we could turn that cosecant into 1 over sine x times, and I'm going to make this a negative sine squared over 1, so it is in the form of a fraction. Ooh, now look what's going to happen here. We could either cancel right now on the diagonal, or if we multiply straight across, we're going to have negative sine squared over sine. Okay, now think back to algebra. What if you had x squared over x? Well, we could simplify by canceling an x in the numerator and then turning our x in the denominator into a 1. So that would simplify down to just x. Same thing's going to happen here with the signs. We are going to keep our negative. But here we would subtract exponents. We're dividing the same base, sine over sine, so we subtract the exponents. 2 minus 1 is 1. So negative sine of x is the exact same thing as all of this. Those are equivalent expressions. Okay, let's do another example. Example 3. Okay, now here factor. It says factor. You're used to factoring algebraic expressions, but this trig stuff is new. So what if we had a question like this, but what if it was just x squared minus 1? How would you factor x squared minus 1? Well, that's just going to be a sum and a difference. X plus 1, x minus 1. We're going to do the same idea here. You know, if I set up an empty set of parentheses, my first term is a secant squared. The only way we're going to get that is a secant theta times another secant theta. So that'll give us our secant squared. And there's no middle term. And then we have a minus 1. So that has to come from a plus 1 times a minus 1. And we can't do much with it now, but we did factor it. At some point, I think it's in section 4, we'll actually, you know, if this is equal to 0, we'll set those equal to 0 and actually solve it. But we're taking baby steps. Here we're just factoring. Okay, now this one, 4 tan squared plus 1 tan minus 3. The tans are different. They might be throwing you. But what if I asked you to factor 4x squared plus 1x minus 3. Minus 3. Okay, well this, you know, we've factored this before in the algebraic sections. I know a lot of people lean toward the ACB method. I'm an old timer, so I would old school just, do a little trial and error. I would first assume this 4x squared has to be a 4x and an x. Next, I would try 2 times 2. And let's see, we have a plus in the middle and a minus at the end, so our signs could be pluses and minuses. We're not sure, so it comes down to the 3. 3 times 1 is 3. If I put my 3 over here and my 1 here, my outers would be a 12 and my inners a 1. That's nowhere close to getting to a 1 in the middle. So then I'd switch them. I'm going to put my 1 over here and my 3 here. So now my outers are a 4x, my inners are a 3x. How would I add or subtract those to get a plus 1 in the middle? Well, this would have to be a plus 4x, and this would be a minus 3. So to multiply these and get a minus 3, that would have to be a minus 3, and that would make this a plus 1. Okay, since I've done it now with the x's, I can now put back in the tans. So this 4x minus 3 is really 4 tan of x minus 3. And x plus 1 is going to be the tan of x plus 1. And it's factored. Okay, what's this algebra help down here? In example 3, you factor difference of 2 squares, and you factor, if you want to review those techniques, you can go back and watch my videos, like, comment, and subscribe, or check out the appendix in the book, either the hard copy or on WebAssign. Here is a team huddle for you. I believe this is the end of this. Yeah. So pause the video and try these, and then start it back up and see if you got them right. Okay. Okay, this first one, it's a lot like 1 minus x squared. I would just set up some empty parentheses. The 1 has to be 1 times 1. And how do you get cos squared? It's got to be cos theta times cos theta. Oop, 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 oop. Why am I putting squares on there? Cos, that's supposed to be an s. Cos theta. Cos theta. How do you multiply those out and not get a middle term? Well, one's got to be a sum. The other's got to be a difference. 1 plus cos times 1 minus cos. Okay, and the last one, I'm just going to crunch it out, set up some empty parentheses. 2 cos squared has to be 2 cosecant squared. Has to be 2 cosecant theta times another cosecant theta. Now I love this because the middle term is minus and the last term is plus, so these have to be minuses to add up to a negative and multiply to a positive. And we can break up 6 as 6 and 1 or 2 and 3. A little trial and error means we're going to have the 3 here and the 2 here. 2 cosecant theta minus 3 times 2 or cosecant minus 2. All right, and that is that. Here is the assignment for this section, page 353 in the book. A nice chunk of even numbered problems for you. The next time we're together in class, we will do some odd problems. Like to get ready for 10, we'll do number 9. We'll do 19 and 21. 19 to get ready for this, 21 to get ready for this. Okay, I will see you in the next video.